Hello, can you please confirm that you can hear me?
Yes,
Yes,
sir.
sir.
Thank you. I hope all of you can see the presentation as well. So let me just briefly recall a few things. Please just confirm that you can also see the presentation. Hello.
Yes, sir.
Okay,
Yes, sir.
thank you. Uh, so in the last class, I will just briefly recall something. We took up the method of images whereby you have a plane, a conducting plane, let's say a copper sheet that is extended all the way up to infinity. That's an idealization, but let's think of it like that for convenience, mathematical convenience at least. It's extended all the way to infinity, both along the x and the y directions. And above the plane, at a height d, you place a point charge q. This will induce charges in the plane and create a potential effect, a potential, or add an extra correction, and a correction to the potential that would have happened only due to this point charge. So the equivalent problem of solving the plane and this positive point charge is this, that you take, instead of the point charge and the plane, you take the point charge itself and its image charge, which really doesn't exist. So the equivalent problem is one of a point charge and its oppositely sign, and its image charge of the opposite sign. So, and then we found out a whole lot of things. This was the case of solving something by the method of images. So that said, we now extend the discussion. So that was what we did, the method of images, the simplest possible case of a point charge located above an infinitely extended conducting plane. Okay, that, just can you please give me a minute? Yes, sorry, thank you. Yes, right. So the extension of that discussion will be to the case of an electric dipole. Remember, we are all trying to solve, in all of these problems, we are trying to find out the potential. The discussion is potential, additional properties, right? I mean, prior to this set of notes, we talked about finding out potential with the help of Poisson and Laplace's equation. So now we have extended the discussion to something more involved. First, we looked at the method of images, whereby, as I said, you are just talking about, physically speaking, there is only one point charge and a plane which is not charged overall. It's an overall charge neutral plane, but because of the presence of the point charge in the vicinity, the plane induces charges locally. Overall, the plane is still charge neutral. It's just that the positive charges have been driven far out and the negative charges have been gathered towards the center. But the sum total of all the positive and negative charges in the plane is still the same, whatever it is. But locally, the inducement of the negative charges, induction of the negative charges locally, will give rise to some additional effect in the potential. Okay, so having finished that point, we now look at a situation whereby you actually have two charges. It's not like this problem whereby you have a charge and its imaginary image on the other side of a plane with the opposite sign. It's nothing like that. You actually have a positive charge and a negative charge. Such a situation gives you what is known as an electric dipole. The the prefix di means two. Pole means a point. For instance, you have a north pole and a south pole. In the case of a magnet, in the case of the earth. So here, earlier, when you were talking about a single point charge, you were talking about a monopole, so to speak. But now you are talking about two charges of the opposite sign separated from each other by a displacement d. Okay, this is very different. Physically speaking, this is different from this situation whereby you have a positive charge up here and you have its image. So this is, to borrow the phrase of geometrical optics, you have an object and you have an image. But the image really doesn't exist. So that's why you say virtual, real, virtual, all those terms are used in the case of object and image in geometrical optics. But here, meaning that when you look yourself in a mirror, it is not just that there is another person exactly like you. Well, not exactly like you. The left goes to right and the right goes to the left. But there's no real existence of another person like you with an exchange of the left-right symmetry on the other side of the mirror. But here in the case of a dipole, you do have two real charges, one positive charge q and another negative charge q. And the separation distance between the two is d, but you are splitting that right down the halfway mark, the middle point, and you are saying d by 2 here and d by 2 here. Okay, I hope you have understood the point. Now, here is a point P, which is very far away from the position of these two charges, the plus charge q and the minus charge q. Okay, the position of point P from the plus charge q is r plus, and the position of P from the minus charge, the negative charge, minus q, is r minus. This position is located midway between the shortest path joining the two charges, and from this point, the displacement to the position P is vector r. Okay, so what is the, I have made a slight I have made an error in the diagram. I'll just clarify that error as well. What is the potential at this point, P? Remember, P is at a distance r from the line, from the midpoint of the line joining the two charges, q and q minus q. And this distance r is very much greater than d. So very much greater than d. Okay. And of course, there's also this angle theta to be noted, and the other angle, 180 degree minus theta, to be noted as well. Now, at this position P, the potential due to this charge is q divided by 4 pi epsilon naught r plus. From here to here, the displacement vector is r plus. And from here to here, the displacement vector is r minus. So, and this charge is minus q. So the total potential due to these two real charges, we are no longer talking about an object and an image, as in this case, but the idea can be extended. So the total potential at this point due to these two charges is given by this formula. Q divided by 4 pi epsilon naught r plus minus q, or minus q, just minus q. But I think it would have been better to write plus of minus q. Yeah, probably that. So minus q divided by 4 pi epsilon naught r minus. So that is what you have. Now what we shall do is to apply the law of cosines. And it is here that I'll point out the error in this diagram. We shall have to find r plus. And from here to here, if I have to go, it should be, this vector is important for us. So it is like you're going down this way and then going this way. And these arrows should be inwardly directed. These two arrows should be inwardly directed to indicate two things. The first thing is that from here to here, and then from here to here, if you go by two vector paths, then the resultant vector will be this, r plus. So that is one thing. And similarly, if this arrow is inwardly directed, then from here to here, and then from here to here, if you travel by these two vector paths, minus q to the midpoint, and then from the midpoint to p along the vector path r, if you travel, then the resultant vector will be r minus. Okay, fine. Now, so these two arrows have to be inverted. In my hurry, I drew the wrong directions. Also, it should indicate something else, that plus q and minus q are attracting each other. So the force acting between these two will be inward, not outward. So the arrowheads, inward turning arrowheads will indicate these two things. Anyway, so I'll correct this note and give it to you later. So what I'd like to do now is to apply the law of cosines to this triangle whose arms have the length d by 2, r plus, and just r. Okay, so by the law of cosines, let us see. See, this is just a generalized extension of Pythagoras' theorem. How so? Let us see. This thing, r plus squared, will be equal to r squared plus d by 2 squared minus 2r d by 2 cos theta. This is law of cosines. I hope you are aware of that. You should be. Incidentally, if this theta were to be 90 degrees, then cos theta would have been 0, and you would have simply got the standard and well-known Pythagoras theorem. R plus squared would have been equal to r squared plus d by 2 whole squared. So that is what it is. So anyway, the 2's cancel out, and you have just minus rd cos theta. Similarly, for this arm, remember this arrow is going inward. This and then this. And this is the resultant vector, r minus. R minus squared is equal to r squared plus d by 2 squared minus 2 into r into d by 2 into cos of this angle, 180 degrees minus theta. I hope you are understanding the logic of this discussion. It shouldn't be too difficult, really. So there we are. So we have these two things. Now, trigonometric rules will tell you that cos of 180 degree minus theta is minus cos theta. Fine. If that is so, then this minus here, minus cos 180 degree minus theta could be written as minus cos theta. Minus cos theta into minus will give you plus. 2 and 2 will cancel, and so you'll just have plus rd cos theta. And so this is r plus squared is equal to r squared plus d by 2 whole squared minus rd cos theta. This here gives this, and this formula in the box gives this. R minus squared is equal to r squared plus d by 2 squared plus rd cos theta. Where's this plus coming from? You already have a minus. That comes from the law of cosines. And then cos 180 degree minus theta will give you minus cos theta, minus and minus will give you plus rd cos theta. Okay, next task. We'll just look at the first formula, the formula that contains the plus sign, r plus squared. R plus squared, we are taking r squared as a common factor, r squared into 1 minus. So I have taken an r squared out of this thing. So there will be we have taken an r squared out of this thing. So it will be d by r whole squared, and this half will give you 1/4 on squaring. And then from this thing, you will get minus d by r cos theta. Basically, what I have done is that I have kind of multiplied this thing by r squared and divided by r. So I'm writing the single r here as r squared by r, and the d by r stays and the r square goes out. Similarly here, I multiplied this thing by r squared and divided by r squared and taken the r squared outside. And so there you are. So here we are now. Okay, But why are we interested in this R plus? Because we have to substitute it here. But here we actually have got the inverse of R plus, Q, or rather 1 by R plus. The Q and the Q here is a common factor that can go out. So it will be 1 by R plus minus 1 by R minus. So that is what we have to do. So basically what we do now is that we take the square root of this equation, and then invert it. And what we shall get is 1 by R plus is equal to 1 by R. And then this whole thing into the square bracket. Remember, it has to be square rooted and inverted. Therefore, it will pick up a power of minus half. This whole thing in the square bracket will do that. Okay, we are not done yet. Then we apply an approximation. You notice that this is not an equal to sign. This is an approximately equal to sign. What is the approximation? We have neglected this d by r squared. Why so? Let us try to understand. We have just kept it's 1 minus d cos theta by r, or d by r cos theta, and then plus 1 by 4 d by r whole squared. So this term I have dropped out, and I've just kept 1 minus d by r cos theta. Why so? And then, of course, there's a bit of a scribbling, but I hope you can see it still. This power of minus half stays. There's a power of minus half here. That stays. Okay, so why have we neglected this thing? Let's try to go back to the geometry. This distance, r, is much, although it's not so clear from this diagram, this distance is much greater than this whole distance, the separation distance between the two charges, plus q and minus q. That separation distance is small d. And r is the line that is the vector that goes to the point P from the midpoint of the line joining the two charges plus q and minus q. Plus q and minus q are joined by a line. So the midpoint of the line is here. And this line is from this midpoint, we are extending the vector r to the point P. That is what you have. Now, I said that this r is very much greater than d, fine. Therefore, d is very much less than r. Therefore, d by r both have the dimension of length. D by r is a small number. And if a number is small, then its higher power can be neglected against its lower power. Be clear in understanding that fact. What do I mean by that? If a number is small, its higher power can be neglected against its lower power. What is that supposed to mean? This is what is supposed to mean. Try to follow the logic carefully. You take a number, when I say a number is small, it should be much smaller than 1, would say. When I say a number is large, it should be much larger than 1. Okay, that's the 1 is the scale. Suppose you take the number 2. 2 is greater than 1, right? So the first power of 2 is 2. 2 raised to 1 is 2. Second power of 2 is 4. 2 raised to 2 is 4. The third power of 2 is 8. 2 raised to 3, 2 to the power of 3 is 8. 2 cubed is 8. So as you can see, you've taken the number 2, which is not a small number. It's a number that is greater than 1. You take that number and you take its higher powers. And so you can see that the higher powers are going to be larger than the lower powers. Therefore, you cannot neglect the higher powers against the lower powers. Okay, fine. What about the other way around? Suppose you have taken a number that is less than 1. Let's say half, 1 by 2. 1 by 2 is the inverse of 2. So you have half. Half raised to 1 is 1 by 2 itself. Okay, half raised to 2, that is half squared, will be 1 divided by 4. So half raised to 1 is 0.5, 2. Sorry, 1 by 2, that's equal to 0.5. Half raised to 2, half to the power of 2 is 1 by 4, that is 0.25. We've already can see that the higher power has become smaller than the lower power. Half raised to 3, 1 by 2 cubed, that is 1 by 8, so 0.125. So 0.5, 0.25, 0.125, and like that you keep going to smaller and smaller values. What is the moral of the story? That if you have a number that is less than 1, let's say between 0 and 1, if both the numbers, as it should be in this case, D and R are both positive. Okay, because they're lengths after all. This is a length and this is a length. So both are lengths, both are positive, but D is very much less than R. Therefore, D by R is a number that is much smaller than 1, but greater than 0. It's a positive number. This ratio is positive, but much smaller than 1. If that is so, then its higher power can be neglected against the lower power. It's much smaller than 1 by 10, 1 by, I don't know, not even probably 1 by, if you, incidentally, if you take 1 by 10, square of 1 by 10 is 1 upon 100, right? So that's 1%. 1 by 10 is 10%, 1 by 100 is 1%, like that. So the higher powers can have become smaller compared to the lower power. So d by r squared can be neglected against d by r. And you can very well ask me, what about the cos theta part? Well, cos theta doesn't make much of a difference here because cos theta can only go from -1 to +1. So cos theta has got a small enough value that's there, but it's not really a significantly small something. Okay, so if that is the situation, then this whole thing, the smallness of d by r, will be controlled by itself only and not by cos theta. Okay, so when you have this thing, 1 by r plus is approximately equal to 1 by r into 1 minus d by r cos theta. This term you have neglected. What's the next thing that you're doing? You are applying the binomial theorem now. You have a small number, let's say 1 plus x. X is very small compared to 1. You have written 1 plus x, and then you're raising this whole thing to the power n. 1 plus x, whole thing raised to the power n, will give you 1 plus nx plus some higher power of x, x squared, x cubed, like that, successive powers. But if x is small, as d by r should be, then d by r, the next higher power can be neglected, and like that it goes on. So basically, you can just write this thing as, you follow this argument carefully, 1 by r plus here on the left hand side is here 1 by r plus, approximately equal to 1 upon r, 1 upon r. This is this formula in the box is the key result here. Then you have 1 here, you have 1 here, minus d by r cos theta, whole thing raised to minus half. This minus half is being multiplied by this thing, and you'll get minus half into minus d by r cos theta will become plus half d by r cos theta. This is the binomial application of the binomial theorem. You have 1 plus x, such as this 1 minus d by r cos theta. D by r cos theta minus d by r cos theta is like your x. 1 plus x raised to n, where n is minus half here. So if you have 1 plus x raised to n, and x is very much less than 1, then all you have to do is just write it approximately as 1 plus n times x. That is what we have done over here. 1 plus n times x. So n is minus half, x is minus d by r cos theta. So the product of the two minus half into this thing will be half d by r cos theta. That is the binomial expansion. So this is an important result which we shall use. Now we go for r minus. The same logic that we have to apply here. R minus squared is equal to r squared plus d by 2 squared plus r d cos theta. So when you have this, when you take this r minus thing, it will be r minus squared, r squared. I'm taking a common factor of, I mean, just whatever I have done for the r plus, you'll do the same thing for the r minus. R squared, 1 plus d by r cos theta plus 1 by 4 d by r squared. Okay. Again, I'm neglecting the d by r squared against the d by r, and that is what you have here. After that, I'm inverting these two and taking the square root of it. So 1 by r minus is equal to 1 by r plus into 1 plus d cos theta by r raised to minus half. And then this into this will give you 1 by r into 1 minus 1 by 2 d cos theta by r. This is the binomial theorem when you have d is very much less than r. Okay, so you have got this 1 by r plus and 1 by r minus here. So q, you take out q by 4 pi epsilon naught divide into 1 by r plus minus 1 by r minus. So this thing, 1 by r plus minus 1 by r minus, you have these two things. This minus this. 1 by r continues to be a common factor. You have got 1 plus half d cos theta by r minus 1 minus, remember, there's this minus sign over here. So when I put a minus sign here, you'll have a minus 1 and plus d cos theta by 2r. So the 1 and the 1 will cancel out because of this minus sign. And you have d cos theta by 2r plus d cos theta by 2r, which is d cos theta by r. Okay, if that is so, you have d cos theta by r, and there's a 1 upon r outside. So this whole package should give you d cos theta by 2r squared. I'm sorry, d cos theta by r squared, because half and half will add up to 1. So d cos theta by r squared. And what have we got over here? You have got q by 4 pi epsilon naught. When you put these two things together, you will get the potential as q by 4 pi epsilon naught d cos theta by r squared. This is the potential due to an electric dipole, a plus charge q and a minus charge q, separated by a distance d. A few points I should now like to discuss about this formula that we have got at the end. QD cos theta 4 pi epsilon naught r squared. Okay, so what do we make of this? First of all, if you had just a point charge, be careful in understanding this thing. If you had just a point charge, nothing else, only one charge, not a dipole. A dipole meaning two poles, right? Whereas instead of we have a single point like charge, you call that thing a monopole. So you have a single point like charge, Q, and what is the potential due to that point like charge? It shall be Q divided by 4 pi epsilon naught R. That is the formula we have written over here. Instead of two charges, if we had just had one charge, Q divided by 4 pi epsilon naught R. That is what would have been there. But here, now you notice we have an R squared in the denominator. So dimensionally, there must be a dimensional length in the numerator as well. A factor of d by r is a dimensionless factor. So basically this thing, and cos theta of course is anyway a dimensionless quantity. Cos theta is the ratio of two lengths. In a right angle triangle, it is the base upon the hypotenuse. Right, so cos theta is anyway a dimensionless quantity. D by r is also a dimensionless quantity. So basically dimensionally it is still the same thing. Q divided by 4 pi epsilon naught, a length dimension. That much is there. Later in one of your tutorials, probably next week, you will be given a problem like this. When we have worked on this problem, you notice that we have neglected all the higher powers. But what if we did not neglect the higher power of d by r? We have neglected the higher power of d by r in this formula. Similarly, we have neglected the higher power of d by r in this binomial expansion. So if we had not neglected that, then what would have been the result? That's another problem for us to take up, but it will be a part of your tutorials. So next week, maybe we will do that. But this is the idea of a dipole. What is the potential due to a dipole? The potential due to a dipole with respect to a point that is midway between the two charges, this distance is r. Our final formula, be it understood clearly, is in terms of d and R and cos theta. dr cos theta. So final formula is in terms of that only. So this and this angle theta. So that is the formula. That's the idea of an electric dipole and the potential that arises due to an electric dipole. So we have finished this discussion. As I said, there's a mistake in the diagram over here. The arrows should be inverted. I'll correct that mistake and I'll give it to you. I've also, in the last class, I pointed out there were two other mistakes. Here, this thing should be a plus. This thing should be a plus in page A4. And up here, this thing in this diagram, this should be z-axis. So I'll correct all those things and I'll upload the notes soon enough, a corrected set of notes. So with this, we finish the discussion of the problem of finding potential. We have had a long discussion on potentials, potential work done, then solving Poisson's equation, solving Laplace's equation. Then we have talked about finding out the potential by the application of the method of images, then finding out the potential of an electric dipole. We are no longer talking about a single point like charge, but suppose you have got two charges, then you have got a dipole over here. So those are the things we have talked about. Now I shall stop this discussion and move on to a new topic, which is related to what we have just finished talking about. That is an electric dipole. So let me stop this discussion. And there is something else I should also like to tell you. This discussion that we have just finished goes on an additional set of notes with the page marking A1 to A6. We have just finished all this method of images and dipole, etc. This whole business. These have been marked with pages having the letter A as in additional. Now, I will start the discussion. I mean, you may be a little confused by something, but I shall clarify it right away. Let's see. I hope all of you can hear me clearly and also see the presentation. Let us see. Can you please confirm that you can see the presentation? Some of you, please just confirm that you can see it.
Yes.
Okay, thank you very much. Please mute the mic. I shall begin the discussion. Please just make a note of something before I start. The last topic was on the method of images and dipoles. They will go from page number A1 to A6, pages A1 to A6. Prior to that, we had finished talking about Poisson and Laplace's equation. Just listen to me carefully and write a few things. The notes of Poisson and Laplace's equation will end at page number 102 in my handwritten notes, page number 102. The sequence of the lecture flow will be thereafter, after you've gone up to page 102, then A1 to A6, all the topics that we have just finished discussing, method of images, dipoles, all that. Page number A1 to A6. Then we start with page 121. Now you will very well ask me, what about pages 103 to 120? Yes, pages 103 to 120 is about magnetostatics in free space, and that's in vacuum. But we have decided to change the lecture flow a little, and this is something to do with electricity in materials. So far, we have talked about point charges placed in vacuum, conductors and stuff like that. But what about dielectric materials? So electricity in materials we cover here, and then we will go back to pages 103 to 120 and start with magnetostatics. So practically we are now nearing the end of dielectrics. I'll maybe sending you a mail to clarify it. Whatever it is, just note the main set sequence number. All of those things that we finished, Poisson, Laplace, all of those things were in main set of notes number 8. After that, main set of notes number 9 will contain images and dipoles. And then this that we are beginning to discuss from page 121 will be main set of notes number 10. So the tag that you should follow will be the main set note number. That will be in proper sequence. Just follow. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we are just beginning to discuss 10. There may be a little bit of shuffling in the page numbering in the main sets, but don't be thrown off by that. Anyway, if you have any doubts, you can clarify from me later. First, let me just finish all these discussion, and then I'll upload the notes. That way you'll have a clear understanding. Okay, anyway, so let us begin the discussion on dielectrics. What is it? That's the opposite of opposite of conductors. We have had some discussion of conductors earlier. Now we begin the discussion of insulators. Dielectric materials are insulators. You notice something, the word di as in dipole, or the prefix di as in dipole. So dielectrics, meaning two kind of charges are there. So insulators are like those things only. And how are insulators different from conductors? That insulators do not have free electrons. Such as metals have free electrons, insulators do not have free electrons, right? So there are no free electrons as you would get in metals. Metals have free electrons, and that's why the free electrons, free, what do I mean by free? Meaning that they are not bound. And if they are not bound, they can move around. How will they move around? On the application of a potential difference. That is what it is. So, on the application of a potential difference, charges can move around. Just like, once again, let me go back to a mechanical example, not an electrical example, and a mechanical example. If your room, I mean, in your room right now, you're probably listening to this lecture, sitting at a table, and the tabletop is flat. All the things on the tabletop are where they should be. They are not moving this way or that. As you lift one end of the tabletop, you create a potential difference. And under the potential difference, the things start moving around. So the things that move around on the application of a potential difference have a tendency towards freedom. You just have to give them a reason to move freely around. And what is that reason? A potential difference. And so it is in the case of a metal wire, let us say a copper. Let me just discuss a metal part a little, and then we'll come back to insulators. A good metal conductor, metallic conductor, copper, let us say. Copper has got a whole lot of free electrons. Remember, the free electrons are coming when the copper atoms form bonds among themselves, and in the process of forming bonds, they give up free electrons. They give up electrons. And I hope also you remember from your school chemistry that copper has got two valencies, cuprous and cupric, 2 and 3, meaning copper is capable of giving up a good lot of electrons, each copper atom, 2, 3, whatever, like that. And so suddenly, with all the atoms in a copper lattice having bonded with one another, and I mean, they will go into the ionic form, ionic stage, and each of these atoms will give out electrons, more than one electron, and these electrons will then move around, free electrons, they will move around on the application of a potential difference, and the flow of these electrons will give rise to a current. However, be also careful to note one fact. By definition, a current is not the flow of negative charges. Electrons are negatively charged particles. So the electrons may be moving, yes, on the application of a potential difference, but what actually is to be read as in your calculations or anything that you do is the movement of positive charges in the opposite direction, an equivalent number of positive charges in the opposite direction. Because the idea of current came much before current as a movement of charges came much before the idea of electrons in an atom and an electron, free electrons in a metallic crystal and all those things. I mean, the idea of a current is what, I mean, electron and all these atom things, these were discovered in the early 1900s, whereas the idea of a current and all those things go about 100 years at the very least prior to that. So that's why people frame the idea of a current without knowing exactly how a current goes on at the microscopic physical level. Anyway, so that is the idea of free electrons and the movement of a current. What about an insulator? In an insulator, now you follow carefully, in an insulator, the atoms that form the insulating material do not give up free electrons. So all the charge particles that ought to give a current through a free flow, all those charge particles are bound. And if they're bound, then they can't move. And if they can't move, there will be no current. So basically, in a dielectric, as in an insulator, they are bound to the electrons are all bound to the atom or the molecule. Unlike in the case of a good metallic conductor, where the electrons can move around freely within the frame of the metallic crystal lattice. Once again, I stress the freedom is qualified, that they can't move out of the metal block. They can move freely within the metal lattice, but not out of it. Just like you, as a citizen of India, can move freely anywhere within the state of India, maybe not so freely in Kashmir, whatever. But theoretically, you're free to move anywhere within the state of India, but you're not free to move out of the border of India and go over to Pakistan or China or these places. Right. So your freedom has got a certain restriction, a limitation. So I hope you have heard of the term dielectrics, because they are used in capacitors. Between the two plates of a capacitor, you fill the space between the two plates of a capacitor with a dielectric material. A dielectric is an insulator. Let's just put it that way. We have already discussed conductors. We have discussed currents. Now we are talking about insulators. Now let us look at certain properties of insulators. The electrons are strongly bound to the atom in an insulating material, the atoms of the insulating material. But as I said, just like in the case of free electrons in a metal, the freedom has got certain restrictions. The restriction being that they can't leave the metal lattice. They may be free to move around within the metal lattice, but not go out of it. Similarly, the electrons that are bound to the atoms of a dielectric material are also not completely bound. Just like the free electrons in a good metallic conductor are not completely free. The freedom is qualified. Similarly, the state of bondage of the electrons in the case of an insulator is also not too bad either. They may be bound, that is to say, they may be jailed, but within the jail premises, they can move around. Just like, let us say, right now, the famous case of Aryan Khan, who is in jail. There's so much talk that is he allowed to move freely within the jail premises and all that stuff. So it's just like that. You may be in jail, but you are not put in chains and bound to one corner of your prison cell. Meaning that within the jail premises, you can stroll about. And that effect is important. In the case of the electrons that are bound to the atoms in an insulator. Why? Because this can still move around a little. Bound they may be. Bound in the sense that they can't move out of the influence of their parent atom and go out freely. They are bound within the atom. Fine, that is all right. But even within the atom, they can still shift this way or that a little. And this process gives rise to the effect of polarization under an electric field. Let us try to understand this thing. First, let us, with a very simple diagram, look at what polarization can be like. Here, I have a diagram. I hope all of you can see the diagram clearly. There are three circles, a black circle in the middle, and then a green circle to the left and a red circle to the right. Let us try to see what they mean. First, let us concentrate on the black circle and completely ignore anything that comes with either the red or the green color. Let us see. Here we have a black circle, and here we have a black dot at the center. Neither of these two things, the black dot at the center and the black circle going around it, with this black circle is centered on the black dot. Neither of them has either the red or the green color. Okay, what is that? That is a diagrammatic representation of an atom. The black dot at the center is the central nucleus of the atom, and the black circle going all around is a representation of the electrons or the electron cloud that is going around the center. There is, I mean, it is not completely correct to see the electrons as point-like particles going round and round about the center. You should see the electron as an a cloud, a diffuse cloud of negative charge all around. But why that should happen is a matter of serious question that gave rise to the subject of quantum mechanics. But I hope in school chemistry you would have read about this thing, electron cloud. So this black circle is a representation of that electron cloud, and the black dot is the positively charged nucleus of the atom. Okay. Now, suddenly an electric field comes from the left and goes to the right. This is the arrow of that electric field. This is the electric field. It's an external electric field created by some charge far away to the left, whatever. Let's say some positive charge far away to the left. And what do positive charges do? Positive charges throw out electric field lines. So here's one such electric field line going past. Now, I have told you earlier the feature of an electric field. The electric effect of an electric field is to, don't forget something, the effect of an electric field is to, if it encounters any charges along its path, it will sweep the positive charges forward. Just like if you have cleaned your room or anything with a broom or a mop, whatever, you sweep all the dust and dirt lying on the floor, and the broom or the mop will sweep all the material ahead of it. So does an electric field behave. It sweeps all positive charges ahead of it and drags all negative charges in the opposite direction. As a result, what will happen is the following. Follow carefully. All the positive charges at the central nucleus, earlier this black dot was the position of the positive charge, positively charged nucleus. Now this positively charged nucleus will be pushed forward by the electric field going in the opposite, going from the left to the right. So the black dot will be shifted to the right at this red dot position. It's got a plus sign, so I've written a plus over here, although I hope, and I don't know whether you can see it clearly or not, but you should just have a clear understanding of it. So the position of the black dot has shifted a little to the right. And what about the black circle here? The black circle is made up of negatively charged particles, and that will be dragged a little to the left. So basically, the nucleus will be shifted in the direction of the electric field, and the electron cloud will be shifted in the opposite direction, backward. Now, earlier, again, I'm asking you to ignore anything with red and green color. Earlier, the black dot, which is the positively charged nucleus, coincided with the average position of this circle. If you take all the electrons, the average position of all the electrons would have coincided with the black dot. The electrons are going round and round in circle. You take their average position. You'll say that, no, instead of a circle, I want to see the electrons in terms of one point-like position. And you can then collapse, since this is a circle, you can collapse all the electrons at the center. And this average position of the electrons would coincide with the average position of the point, with the real position or the existing position of the point-like positively charged nucleus. So they would have coincided. But now, with the application of this external electric field, it would look like that the position of the nucleus has shifted a little to the right, and the position of all the electrons has shifted a little to the left, and the average position of the electrons is now by this green dot here with a minus sign a bit to the left, and the nucleus, there are two ways of looking at it. Sorry, somebody please mute the mic. What is the matter? Mihir Kumar, please mute the mic. I have done that for you. Okay. So there are two ways of looking at it. Either you look at the electron cloud as collapsed at the center so that its average position coincides with the nucleus, or you can look at it in the other way. You expand the nucleus and make it coincide with the electron cloud. So that way, the nucleus could be expanded in all direction and it would have coincided with the electron cloud. So if you represent the nucleus by this red circle, the red circle would have shifted a little to the right, whose earlier position was the black circle, and the green circle would have shifted a little to the left, whose earlier position was again the same black circle. Or if you look at it in terms of points, the black dot, which was the position of the nucleus and the average position of the electron cloud, that black dot has now been separated. A red dot has gone to the right and a green dot has gone to the left. So the red dot is the positively charged end and the green dot is the negatively charged end. What have you got over here? Earlier you had a point-like object. Now it has been split into a separate plus end and a minus end. Of positive and negative charges. Some words have been written all around. Let us see. We are looking at an atom that has got a positively charged center and a negatively charged electron cloud around it. If the electric field had not come from the left and gone on to the right, then this separation of positive and negative charges would not have taken place. I hope we are clear on that point. If that separation had not taken place, then the atom would have maintained its old symmetric configuration. So this separation has happened because of the distortion brought about by the electric field. So this is polarization by distortion. Otherwise, this thing does not have any permanent dipole-like behavior. The atom doesn't have a dipole. It has got a positively charged center, a nucleus, and surrounding that nucleus, you have an electron cloud whose average position will coincide with that of the nucleus at the center. So there is no permanent dipole in an atom. You apply an electric field, you stretch the atom a little to the right and a little to the left, and you create a separation of a positive end and a negative end, a separated positive end and a negative end, and as such, instead of a point-like object, earlier you have an elongated structure. That is the behavior of a dipole. Okay, this thing is on a non-polar dielectric material. What do I mean by non-polar? Something that hasn't got any natural tendency to be polarized. It doesn't have any natural pole. You have to apply some extra force from the outside to create this polarization. It doesn't have any permanent dipole. So that is in the case of an atom. What about molecules? Water, for instance. In water molecules, H2O molecules, they have a an H plus, an O minus, and an H plus. So it's shaped somewhat like a V. The two ends of the V are the positions, or two ends of the arms of V are the positions of the H plus ions, and the vertex of V is the position of the O minus ion. And the H pluses can be seen to have an average position, and as such, there will be a positively charged end and a negatively charged end. Water molecules are already polarized, so they have a permanent dipole, unlike in the case of the atom that we just discussed. And so if they already have a permanent dipole, then what will be the behavior of this dipole under the effect of an electric field? Let us try to see. You look at water molecule. Initially, let us say, I mean, water is not a very good example to discuss. I mean, it is and it is not. What do I mean by that? Water is, of course, a very good example of a polar molecule. I mean, the polar properties of water are extremely important, and when it comes to being such a good solvent, I hope you know that water is a very useful, readily available solvent. Water has got very important properties, right from, let us say, the anomalous expansion of water, all this polar behavior, all of these things. So water is a very astonishingly a helpful liquid, and that is why it should not be surprising that the first thing that we look for when we are searching for life anywhere is the presence of water. Without water, life would not be possible. That's why in the present Mars exploration mission, the explorers are looking for signs of liquid water on planet Mars. That way, you may then be able to look for the presence of life on Mars. Anyway, so as I said, water has got very important polar properties, but then water should not be thought of as readily subjecting and responding itself to and responding to the effect of an electric field. What is this kind of response that I'm talking about? Suppose you have got a container full of water. All the water molecules in this container will be randomly oriented. Remember, one important point I should like to stress is that a dipole has got a positive end and a negative end. Okay. And there are certain vector properties. I'll touch on that vector properties soon. It's called a dipole moment, right? So these these dipoles are randomly oriented initially. Now, as soon as you apply an electric field, let us say an electric field is coming from the left to the right. What will it do? Once again, it will tend to push the positive charges forward and the negative charges backward. You have one such dipole, electric dipole, already permanent electric dipole. Um, what it will do is that here we are. Let's just see. This is not a very clear diagram, but it should help you understand this thing. This arrow is horizontal. Follow carefully this discussion. This arrow indicating the electric field is horizontal. And this is a dipole already formed, a plus end and a minus end. Okay. This arrow is an indication. This arrow joins the plus end with the minus end. And this arrow is not completely aligned with this external electric field. There's a small angle of inclination between the two. Okay. Now what happens is that when the electric field drills through, the positively charged end would tend to move forward and the negatively charged end would tend to move backward. But the molecular bond is very strong, so it's not going to be distorted so easily as in the case of an atom. So instead of stretching this structure, what will happen is that in an effort to align, the plus end would rather undergo a torque and coincide with the direction of this electric field, and the minus end will undergo a torque and go a little up and coincide with the direction of the electric field. As such, this straight line joining the plus end and the minus end will just undergo a slight rotation here and align with the electric field. So this is an alignment effect. So suddenly, earlier, without any external electric field, all these dipoles are randomly oriented. They have random directions in space, plus this way, minus this way, whatever. Suddenly, on the application of an external electric field, and the external electric field is not a very strong field, let's say, because if be too strong, then this thing will get stretched also, and it's not as strong as we would need to bring about that effect. It just has enough strength to bring about, it has enough strength, but it has enough strength to bring about an alignment. So all the positively charged dipoles will rotate and align themselves with the electric field this way, and the negatively charged dipole will rotate in the opposite. So if the plus end goes down this way, the minus end will go up this way. And as a result, the plus and the minus end indicated by the arrow will be parallel to the direction of the electric field. And suddenly, you will see a strong overall polarization of the system. All the molecules will become ordered in their alignment by a rotational effect. There will be a torque, this rotation on alignment. So it's different. So overall, the system will suddenly have positive charges at one end and negative charges at the other. So this will be done by the rotation of all the molecules, rotation or alignment of all the molecules aligned along with the direction of the external electric field. How different is it from the previous discussion? The difference is that, first of all, we are talking about molecules, not atoms, number one. Second, the polarization is not happening at the scale of the molecules, but at the overall scale of the system, where polarization has been brought about due to rotation imposed by the external electric field. And as such, there's a tendency of positive charges at one end and negative charges at the other. But here, the polarization is happening at the level of the atom itself, and it has happened because of the distortion imposed by the external electric field. And the third point is that in this case, if you switch off the electric field, again, just like an elastic string or whatever, it will snap back to its original position. So this distortion will be lost as soon as you switch off this electric field. But here, if you switch off this electric field, the overall polarization may be lost, the alignment may be lost, polarization, and hence the alignment may be lost overall. But the dipoles, the molecules will continue to have their permanent dipole-like features, dipole features. So that will not be lost. So these are happening because of the rotation or alignment of permanent dipoles. Now the question is, I've also added another comment over here, energy is minimized. Now why is the energy minimized? It's because of a very simple principle. You look at this formula I've written over here, potential is minus P dot E, where P is the dipole moment. I'll come to that dipole moment business very soon. E is the external electric field. Now, the natural tendency of a dipole is to align with the direction of the electric field, where the positive charge will be forward in the direction of the electric field and the negative charge will be in the opposite direction. So that will give you the lowermost energy configuration. And the angle between this dipole and the electric field will be 0 degrees. If it is 0 degree, what is a dot product like? A dot product is minus magnitude of P, magnitude of E, cos theta. If theta is 0, cos 0 will be 1. So with a minus sign, you immediately see for yourselves, you can check for yourselves that with the minus sign, that will be the lowest possible energy. If theta is 90 degrees, then it will be 0. But a negative number is lower than 0, smaller than 0. And if it is oppositely aligned, then the angle between the, meaning that the plus is this side and the minus is on the other side, if it is oppositely aligned, then the angle between the two, the electric field and the dipole, will be 180 degrees. Cos of 180 degrees will be minus 1. Minus 1 with the minus already outside will give you an overall positive potential. That will be the highest possible potential energy configuration. So the minimum energy configuration is when cos theta will be 1, that is to say theta will be 0 degrees. It is happening because of this minus sign. That is the definite. But I'll get to this discussion in greater detail shortly. First, let us look at this P business over here. What do I mean by this P? It is known as the dipole moment. Dipole moment, P, is the displacement between the two charges. You have a plus charge and a minus charge. And the displacement between the two charges is a vector. I'll have to be a little more careful in stating something else that I have not written, times the plus charge. This charge, value of the positive charge, multiplied by the displacement between the two charges. Let us say that the positive charge has the value Q, and the displacement between the two charges is d. What is, when you talk about a displacement, now comes something very important. Please follow this point carefully. When you talk about a displacement, you have to specify a source point and a destination point, an initial point and a final point. So if you're talking about a vector starts from somewhere and goes to another point. It has a sense of direction. So in the case of the displacement vector between two poles in a dipole, between two charges in a dipole, is the direction of the displacement, that is the arrow that I have drawn over here. The direction of the displacement will always be from the negative charge to the positive charge. This is the direction of the vector, minus sign to plus sign. This is the direction of the dipole vector. That is the direction of the displacement. I'm sorry. That is the direction of the displacement. But that displacement is multiplied by the scalar value of the charge. Therefore, the direction of the dipole moment, which is defined as the scalar value of the positive charge multiplied by the displacement between the two charges, in which the direction of the displacement is from the negative charge to the positive. Negative is the source, positive is the destination, right? That is how it is defined. That is the displacement. So from minus to plus, that is the displacement. That's the direction of the displacement. Not the direction of the electric field. Be careful about that. Charges, a negative charge will always tend to get electric fields towards field lines towards itself, whereas a positive charge will throw electric field lines out. But here the definition is not about the electric fields of these individual charges, but just the direction of the displacement between the two charges. So that direction is always from the minus sign to the plus sign. So that displacement times the charge, positive charge Q, vector times the scalar, gives you a dipole moment overall. And that will take us back to the idea of the potential energy once again. V is the potential energy minus P into E. P is the dipole moment into the external electric field. Let us go back to this figure once again. P is the dipole moment, E is the external electric field, P dot E. Magnitude of P into magnitude of E into cos theta. If these two things are aligned, theta will be 0. Therefore, it will just be minus PE. Smallest possible value when theta is equal to 0. If theta is equal to 90 degrees, then cos 90 degree will be 0. Potential energy, suppose this is the electric field and the dipole moment is perpendicular to it. That's an odd thing really to happen. And if the opposite happens, that is to say, plus sign goes that way and the minus sign goes this way, you have to do some work to make such a thing happen, because the natural tendency is for the dipoles to align. So if that is to happen, then what will happen? Cos theta will be -1, because the angle trapped between two anti-parallel vectors is 180 degrees. Therefore, with 180 degrees, you will have negative cosine, -1. So minus into this minus already there will be +1. So energy is minimized when the alignment is such that there is an external electric field, the plus end is to the right, the minus end is to the left, and this arrow will be parallel to each other. That is when energy is minimized. Anything else, there will be a tendency to rotate and bring about the alignment. Okay, now a few other extra discussions. Overall, if you apply a very, very weak field, the rotation may not be complete. Just like if you you have the steering wheel of a car. Those of you who drive cars will know. If you have a steering wheel of a car, you can't just give a feather touch to the steering wheel and expect the steering wheel to rotate, right? You have to apply some moderate force for the steering wheel to be rotated. And so it is that if the external electric field is not very strong, then the rotation may not also will not also be a complete rotation. It will just rotate a little. So stronger the electric field, greater will be the this behavior of this dipole behavior, the dipole behavior in all of these problems. I'm sorry. I'm terribly sorry. I made a mistake here. I'm talking about. I shouldn't be talking about the molecules. I'm talking about atoms. I'm sorry. I'm sorry. If you apply a weak electric field, I'm sorry about causing a confusion. If you apply a weak electric field, this distortion may not be too strong. So now you can see, if you go back to the atom, if you apply a strong electric field, stronger will be the separation between the plus end and the minus end. That is what happens. So if that were to be so, then the dipole that is created by the external electric field will be in proportion to the electric field itself. Follow this point carefully. This whole rotation business is this potential energy and all these things is with respect to this rotation business. And maybe I'll clarify these things in the notes a little. But if you look at polarization by distortion, if you apply an external field, it'll bring about the distortion. Stronger the field, greater is the distortion. And like that, it goes. So the dipole that is brought about in a physical system which does not have any permanent dipole will depend on the strength of the electric field. The dipole moment, therefore, will be proportional to the electric field. And this proportional factor is given by alpha, and alpha is known as polarizability, preferably atomic polarizability. We are talking about atoms over here. Atomic polarizability. So this here is atomic polarizability as it pertains to atoms, not molecules. So this rotation business does not apply over here. Because this is a point-like structure anyway. With the electron cloud also, average position of the electron cloud is also a point-like structure. A point does not have any idea of rotation, a concept of rotation. So that is what it is. So that is for an atom, the dipole moment will be proportional to the electric field, externally applied electric field. And I have added a few comments over here. Atoms do not have a permanent dipole moment, but molecules do. In the former case, you say that they are non-polar material. In the latter case, such as in water, you say that they are polar material. Water is known to be a very good polar solvent. Okay, again, let us go back to all this molecular business where you have polar material. So initially, when you have no external field, then the dipoles are randomly oriented. When you apply an external field, the dipoles will be aligned in a preferred direction, namely the direction of the external electric field. And so earlier, when the dipoles are randomly oriented, these dipole vectors will tend to cancel one another out. But when you bring about order in the system through the external electric field, the dipoles will be oriented in one direction and they'll be reinforcing, each vector will be reinforcing the other vectors. So they will be like, they'll all be like soldiers marching in a preferred, give me a minute and I shall finish this point. They'll be like soldiers marching in a preferred direction rather than a mob, unruly mob running helter-skelter. Not, so they will have a sense of direction. So when you add up all the vectors, this summation of all the dipole moments will give you a substantially large vector. So that large vector divided by the total volume of a system, let us say a volume of a water in a container, will give rise to a new vector known as polarization. Earlier, when there was no order, the polarization vector will be nearly zero. It is defined, the polarization vector is defined as the dipole moment per unit volume, or polarization. Earlier, when there was no order, that will be nearly equal to zero, but with order imposed, there will be a substantially large vector sum that divided by the total volume V will give you a vector known as the polarization vector. So this idea is more applicable to molecules, but it can also apply to atoms. But I'm sorry about that little confusion I created. This discussion that P is proportional to the electric field pertains largely to atoms, where distortion is brought about by the electric field, and therefore a substantial dipole moment can only be achieved by a strong external electric field. Anyway, we have run out of time. It's 9:46 now by my computer. I shall stop the sharing. You have any questions, you may ask me. Otherwise, we may leave now. I'll stop the recording as well. If you don't have any questions, we may leave now.